in YouTube. We are streaming now in a few minutes, and the seminar will be recorded. Okay, welcome to the virtual seminar on complexity. This is the first seminar of the new year, 2021, but this is the 8th session so far in the virtual seminar series. You can find all our previous seminars in YouTube, in the channel of the Center for Complexity and Biosystem. As usual, the talk will be around 45 minutes, and we'll have then questions from the public. You can write the question in the chat, or if you are not too many, we can also take the microphone and talk over your camera. So just a few organizational things. So this is, we'll have still this series going on with a bit reduced pace with respect to the previous semester, where we had 2 seminars every 2 weeks. Now what is planned is to have 1 seminar every month. We might add seminars if there is higher demand, but this is more or less the type of program we have. And the next seminar will be in February, in 26th of February, by Bernat Corominas Murtra. But you can find all the program, speakers bio, calendar, abstracts, and so on in the website of the seminar. Today, it's a great pleasure to have here Ginestra Bianconi, whom I know from many years, as she was a student. She graduated in Rome now some years ago, and after a series of travels, so she did a PhD in the US, I think University of Notre Dame, if I'm not mistaken, and then she's now a professor of applied mathematics in London and at Queen Mary University, and also she's a member of the Alan Turing Institute, fellow of the Alan Turing Institute. She did a lot of work in networks, in interdisciplinary application of networks, also more mathematical application of networks. And today she will tell us all about multi-layer networks, so these networks of networks, so you can say, or she will tell us more about it. And I think she wrote also a book about a monograph about multi-layer networks, which is really a big expert on that. And so without further ado, I leave the floor to Ginestra. Thank you.
Thank you so much for this kind introduction. It's a real pleasure to be here virtually together. I don't know if I have to say in Milan or somewhere dislocated around the world. Let me just start sharing my screen. Just a minute. Okay, so it's a real pleasure to tell you some of the research in a field that has been in the last years one of the most vibrant fields in network science, which is multi-layer networks. So here in 2019 we have celebrated the 2018, we have celebrated the 20 years of network science. And in this year, we have gained unprecedented information about complex system with this very simple yet very powerful idea that the complexity of system in biology or in infrastructure are captured by the network of their interaction. And a lot of attention has been focused on the interplay between the structure and dynamics of this network. And we have characterized the fact of statistical and combinatorial property of network, including the degree distribution, and also like geometrical property, like the diameter of this network. the small world property. But it is becoming clear that in order to address the complexity of a large variety of systems, ranging from the brain to the cell, it is important to generalize networks. And one major example of generalization of network is the one of multi-layer networks. So multi-layer networks have been proposed initially by sociologists several years ago to study network like this one. So this is the Florentine families in the Renaissance period, and that are connected via business relation and marriage alliance. And really the network of power between the families is described by this multi-layer network, including these social ties of different nature. And one of the questions here is how central is the node? So how important is, for instance, the Medici family? However, recently we have access to much larger data set. And for instance, if we just consider a social network data set, we have access to something like the APS publication data set, including all publication in American Physical Society in more than 1 century. And as papers have typically keywords or, something like PAX number, it is possible from this large data set to characterize the collaboration network of scientists on different subjects. So each layer is a collaboration of a network of collaboration between scientists on a different topic. For instance, biological physics or geophysics or high energy physics and so on. And as scientists collaborate and work on different topics, one can build a network between this layer, indicating the similarity between the layer. And from this multi-layer network, one can, from the bottom up, reconstruct how knowledge is created in practice by the scientists. So this is one can produce alternative taxonomy that are different from the top-down taxonomy, for instance, of what used to be the taxonomy of PAX number. In transportation network also, multi-layer are ubiquitous, and one example of very widely studied transportation network is the airport transportation network, which we know is fundamental to study epidemic spreading at the level of different countries, at the worldwide level. And but the airport transportation network is actually a multi-layer network where each airline company offers only several flight connections, and the topology of the different layers can be very different. So really, in order to understand how this multi-layer network is constructed and evolved, one needs to understand this factor that for instance, here in this case, different flight connections are operated by different airline companies and correspond to a different design principle of different design companies. But actually, multi-layer networks are now being used a lot also on physical system. And I like very much this paper by the group of Jürgen Kurz and with first author Donge, in which they look at geopotential at different altitudes, and they extracted information about climate with this representation of this data as a multi-layer climate network. And in biology, of course, multi-layer networks are ubiquitous. If you think of like the kind of trajectory that the field has had since starting from single molecule interaction, then in the 2000, there's been the first high throughput experiment focusing on system representation, but of a single type of interaction. So for instance, only is2 hybrid, the result of is2 hybrid experiment of protein interaction. And nowadays is the moment to address problems at the even higher level. So at the cellular level, the cell itself is not alive if it does not, one does not include the fact that all these different type of interaction occur at the same moment in the cell. So if any of this layer is not functioning, the cell is not functioning anymore. So really, when you have a network with links of different color of connotation, for instance, different type of interaction between the molecule in a cell, then you can kind of represent this as a multi-layered network where you distinguish between interaction of the same nature and connotation. So you have different layers in which the interaction have the same meaning, but then you study the globally the structure of this more complex network architecture. In the brain, also multi-layer networks are very, very important. And here I focus in particular at the cellular level. So at the cellular level, neurons interact via synaptic, so chemical connection, but also gap junction, so electrical one. And there is a very interesting paper by the Cambridge group that have a look at C. elegans, and they also consider other layers. So there can be communication in some sense between the neuron due to the release and the reception of monoamide and neuropeptide that they just diffuse. So there is no, is a wireless network because they just diffuse in the C. elegans, and they are received by certain neuron that have, you know, the particular protein expressed. So this network can be extracted from gene expression. So for the moment, I spoke a lot about this multi-layer network perspective, but actually the topology of multi-layer network can vary very, very much. And in general, you can have network of networks, and you distinguish in particular between the interaction within each layer so that they have a given connotation, but there can be also interaction among different layers that are called interlinks. And there is a lot of freedom in general to define the network of network in the way these interlinks are placed, and they can be one-to-one, they can be one-to-many, like in this example. And you, for instance, here, this is a triangle of network of networks. So each node is in one layer is interacting with one node in any of the other two layers, but the nodes are not one-to-one, right? So you can go multiple time in a loop. Here instead they are one-to-one, so you go only once in a triangle. And this really can be shown to change the behavior of dynamical process that you can define in the structure. So this concludes this introduction to why people are interested in multi-layer network and why they are important in order to characterize, model, and predict complex systems. And here I make this advertisement of my book, as Stefano indicated in the introduction. I've been publishing this book for Oxford University Press, in which I try to be very comprehensive and represent the wide interest in this subject and the different point of view and the different way of people have looked at these topologies. Here I want to focus on something that is more strictly related to my research, and in particular I want to introduce two topics. The first one is the relation between multi-layer network and information. And the take-home message wants to be that multiplex network encode more information than their single layer taken in isolation. So I will focus particularly on multiplex networks, which are the most simple example of multi-layer networks. So they don't have all this degree of freedom, although they have some degree of freedom, but not as much as network of networks. So you have a multiplex network formed by M layers, and here, for instance, 3, and each layer is a network formed by M nodes. And each node has a replica node in each layer. So for instance, in a social network, you might say that one represents the same person in a mobile phone, email, or chat network. Or you can say that, you know, for instance, assuming that there is a one-to-one relation between protein and genes, one can represent a protein in one layer and is the protein interaction network, and one can represent the gene of expressing that protein in the other layer. So there are different ways to represent multiplex networks, and I think there is quite of a degree of freedom in the way you want to represent your data, but at the structural level, these three representations are the same. So practically, you have different layers in which you want to represent protein interaction and transcription network, for instance, or more complex biological relation, and so you have two layers like that, or you want to represent this as a colored graph in which you have the nodes interacting via different type of interaction, or you might want to emphasize the fact that the replica node might really mean something different. They might sustain a different dynamics. So in that case, you might want to introduce also this interlink relating replica node, and you might want to give a different meaning to interlink. So for instance, a popular meaning that has been given is in transportation network, if one network is bus and the other is train, for instance, or tube or underground, you want to represent a cost of going from one layer to another, from one station, Oxford Circus tube station, to Oxford Circus bus station, okay? So, and since ultimately really network are a way to encode information, it's very important if you introduce some link and you associate to this link a different meaning. But at the structural level, I mean, these three representations are the same, and the multiplex network in all these cases is represented by a vector of networks. So you have practically a network of a vector of networks, so a graph for each layer between the same set of vertices and having a different set of edges. So as such, they are represented by a vector of adjacency matrix, or a list of adjacency matrix, each one telling you if node I is linked to node J in layer alpha. And this simple representation, however, encodes for a lot of correlations. And for instance, one correlation I've been working on and I found very interesting is the fact of having link overlap. So this is the example of the air transportation network in which I plotted all flight connection operated by more than one airline companies. So in which the link is not only existing in one layer, but more than one. And in order to characterize link overlap between two layers, you can have a global measure measuring all the links that are present simultaneously in layer alpha and in layer alpha prime, or locally for node I, you can say, well, the number of, let's say, friend of node I that are both friend in layer alpha and friend in layer alpha prime. So really, while in a network, you have this notion of link, so the interaction either exists or doesn't not exist. In a multiplex network, you need to extend this notion to multilink, in which you should distinguish all the type of connection that can relate to nodes. And in a duplex network, when you have two layers, node 1 and 2, they can be connected in layer 1 and in layer 2. So we say there is a multilink 1-1 connecting them, or they can be connected in layer 1 but not in layer 2. So we say they are connected by multilink 1-0, and so on exhaustively. You can consider all the combinatorial option that relates any two node. So from this multilink, one can extend the notion of degree. So the degree of the node is the number of links of a node in a simple graph. Here we define the number of multilink vector M incident to a node. So for instance, if you have two layers, we can have Ki10, which is the number of link in layer that node, the number of friends that node I has in layer 1, but not in layer 2. So the number of friends that communicate with node I, for instance, via email, but not mobile phone. K101 is the number of friends that communicate via mobile phone, but not email. And Ki11 is the number of friends that communicates with both means of communication. And this is quite important because if you want to model a multiplex network with link overlap, it's not, it is not, it is, you cannot just draw the network in each layer from a given configuration model, for instance, because in that case you find a negligible link overlap. What you need to do is to generalize the notion of the configuration model by enforcing, instead of the degree sequence, you enforce the multi-degree sequence. So you place some stubs. So here the black is a stub of only in layer 1, but not in layer 2. The green is a stub that is present only in layer 2, and the red is a stub that is present both in layer 1 and in layer 2. And then you match the stub of the same color in such a way that you generate a multiplex network with the desired multi-degree sequence. And alternative, you can have what is called a canonical ensemble, in which instead of constraining the multi-degree sequence as an hard constraint, you enforce a soft constraint. So you calculate the probability that I is connected to J by multilink vector n, and then for every pair of nodes you draw a die, and with that probability you put a multilink vector m between them. So the configuration model is called microcanonical model ensemble, and exponential random graph is called canonical ensemble. So you can really do the statistical mechanics of this, writing the marginal probability, so the probability that two nodes are linked by a multi-link vector m. And this is not factorizable into the contribution of I and j alone, but as long as the multi-degree are not too large, then this marginal probability, they factorize again, and they have the expression that is proportional to the product of the multi-degree of node I and J. So this is the uncorrelated kind of limit. So you can calculate the entropy of this ensemble, which calculates the logarithm of the number of multiplex network present in this structure. And interesting here, in this paper, I revealed that these ensembles are not equivalent, so they differ by an extensive quantity in the case in which we fix the multi-degree sequence. And this is a general outcome of having a number of constraints which is extensive with the number of nodes. And this extends our previous result of 2010, in which we show that this is also true for network. But multilinks can be also used as motifs. So you can use multilinks also and calculate the zeta score of multilinks in a given data set compared to a null model. And with these kind of statistics, you can reveal which kind of pattern of connection between two nodes are in some sense enhanced or suppressed in your real data set. And this is what has been done by these people in the Cambridge group working on C. elegans. And another way to use this tool to extract information is to use the multi-degree itself. And this has been used, the multi-degree has been used to reveal the different role of financial sector in financial crisis by this other work by collaboration between UCL and King's College group. And what we have done instead is that we have studied the correlation between the weight and the overlap. So, so the fact that a multiplex network can be also weighted. So we constructed, as an example of this weighted multiplex network, a network of citation and collaboration. So scientists citing each other and collaborating with each other. And we found that by measuring the multi-strength, so the sum of the weight of the link belonging to a given multi-link, 1, 1 or 0, 1, we find that practically the slope of this regression would tell us the bias of the author in citing the hub. And this slope is higher for multilink 1, 1, indicating that there is a statistical significant way, different statistical way in which scientists cite their collaborator and in respect to the way in which they cite the people that are not their collaborator. And this is a very simple result, kind of expected, but is a proof of concept that with a multiplex network, by simply conditioning, you can extract more information than by considering the single layer in isolation. Because if by looking just at the citation network, you would not have a clue of this difference. So, yeah, I would like to touch on another subject also. I will speed a little bit up, and I will speak about multilayer network and robustness. So, in these multiplex networks, you can give a different meaning to the interlink, and one different meaning is interdependence. So two nodes are interdependent if the damage of one node implies the damage of the other node automatically. And this leads to a extended notion of giant component. Instead of having the giant component, you have the mutually connected giant component formed by all the pair of nodes that are connected to each other by at least one path in each layer. And this mutually connected giant component can be thought to be also the outcome of a process of avalanches spreading back and forth in the different layer and ending up by having only the mutually connected giant component in the multiplex network. So interesting, theoretically, this can be studied with a message passing approach, which has also an epidemic spreading interpretation. And the message passing is known to be defined by this equation on single network. And on multi-layer network, a node sends a positive message saying, I'm connecting you to the mutually connected giant component if it's not initially damaged, and if in all its layers it has at least one neighbor node that also send a positive message to him. So practically, in this epidemic spreading interpretation, a node continues to spread the information, the message, if it receives at least one message in each layer. So it must be infected in every layer in some sense. And the equations are given by this message passing. If you average over an ensemble, for instance, on a Poisson network, you find for a single network the very famous equation, this equation in orange. In a multiplex network in which each layer is Poisson, you find this blue equation where that differs only by this power m, the number of layers. But while here, yes, so when you look at the solution of this equation, practically you look at when sorry? You look at when this equation is equal to 0, the solution of this equation equal to 0. So there is always a 0 solution, but this function has a minimum. So when this, and depending on this ratio, the average degree of the network and P, the probability that the node is not damaged. And when this product is high enough, this minimum touch the x-axis. So the solution of this equation, instead of being 0, jumps to this value and then increases again. And so the transition is really discontinuous. While in simple percolation, we have a continuous transition. When we have two layers, you go from the right to the left as you damage. So the mutually connected component decays at a certain moment, it jumps discontinuously to 0 in a discontinuous hybrid transition. And with 3 layers, the system is even more fragile. So how can we boost the robustness of a multiplex network? Well, this is a problem I've been thinking for some time. And really, while this framework of interdependencies reveal that multiplex network can be more fragile, so this is quite inspiring for studying infrastructure that can be more and more globally connected and more fragile, but is something that is a bit in contradiction with the fact that we find multi-layer in biological system, which would have been not selected if really would correspond to a very fragile structure. So the options are two. Either one gets rid of interdependencies altogether, but this is not really likely because some sort of interdependencies must be there also in biological system. And actually we know that there is a lot of combinatorics both in neuronal dynamics and in the cell. So what the problem that we really wanted to focus on is whether a multiplex network is more or less robust if we add new layer. And the theory, the standard theory, the standard model will tell us that if we have 2, 3, and 4, the system becomes more and more fragile. But what we have done, we have considered is that what happens if we have redundant interdependencies. So if a node is active, if at least in one other layer, one of its replicant node is active. It doesn't require all its replicant node to be active, but only one. So by changing this combinatoric, we have some redundancies in the system. And then as we add the number of layers, the position of the transition, so the average degree at which we have the transition and the size and the jump, while in the standard model they both increase, so the system becomes more and more fragile as we add more layers. In the redundant model, they start from m equal to 2, in which they are exactly the same, but then the system becomes more and more robust. So this idea of including some redundancies can, in some sense, explain why more layer might be favored in this context. So we have the equation, again, message passing, written here diagrammatically, and we applied this, for instance, to the airport network. And here you see in green, 3 airport, a multiplex of 3 layers, in which we have a transition that is at a value of p that is much larger than the transition in the redundant model, which is the purple case, in which we have introduced a redundant interaction. Finally, I want to tell you some recent work that we have been doing, again, addressing the question of robustness. So, and in particular, how can we assess the risk of dramatic failure in real finite multiplex networks? So we have seen here, the theory of this interdependent percolation, which tell us that the transition is discontinuous and abrupt, and there are here at this discontinuous transition, there are big avalanches of failure, dramatic cascade. But then if we look at a data set, for instance, an airport network like that, we find a smooth curve, which doesn't appear to have any sign of discontinuity. And this has been claimed by some that is a signature of the robustness of this real network. But this here, what we plot here is the average size of the mutually connected giant component when the nodes are damaged with probability 1 minus p. But then let's do one iteration, one swap. So we damage the node one after the other, and we monitor the giant component, and we find this result. Okay, so it's different from the mean, but I don't know what we can say. Then we literally do like a handful of other simulation, and we get that. Well, this one is more reminding us about the discontinuous phase transition, and then another one, and we get this one, which if it were the only one, we would say it's a clear indication of a discontinuous transition. So what is happening here? So we approach the problem with a large deviation approach. So we consider the full distribution of size of the mutually connected giant component when the nodes are removed with probability 1 minus p, and we measure the average and the most typical size. And this is the distribution. So this is the distribution for very high p. So we have a mutually connected giant component, which is quite large, around 0.9 of 0.9%, 90% of the network. And now I will show you a movie where this distribution change as a function of p. So we damage more and more node, and we look at the giant component which can end a distribution of the mutually connected giant component we can find. So this distribution moved to the left, but if I rerun this another time, I show you here, well, I show you, yeah, I don't know. You can see clearly that there are a point where the distribution becomes bimodal. So if we plot the average, we have a smooth curve, but if we plot the most likely distribution outcome, at this point, when you have the orange distribution, you jump from 0,3, you jump to essentially 0. So this means that in this case, you have two equally likely outcomes that are very likely, one in which the system is still robust to some extent, and a case in which it's totally dismantled. So the most likely is as this dramatic discontinuous jump. And these two pictures together are giving you more information about what is actually happening than just the average mutually connected giant component. And we look at different data set, airport, also biological data set, and we find always this result. And these data sets are not too big, are just the middle size, around 1,000 nodes. So we have a measure of centrality. We have device, so it's measuring which nodes are more essential to keep to safeguard in order to have a more robust structure. And then when we put ourselves in this condition of maximal uncertainty, in which the outcome of a damage can be either a network that is still existing at 30%, but still existing, or a network that is totally dismantled. And we safeguard just the node that is top rank in this centrality, and the distribution becomes immediately unimodal in this case. So we really safeguard, we avoid this outcome of having a completely disconnected, a completely dismantled network. And if we safeguard 2, 3, and 4 nodes, then this distribution moves also to the right, so the system is even more robust. Finally, we wanted to have a kind of theoretical understanding of what's happening here, because it's known that percolation is self-averaging. So in the large network limit, we should find that the average gives a good indication about the transition, and indeed it's so. So if you have a Poisson duplex network and you change the size, you see that this disagreement between the most likely and the average shrink as we increase the network size. And in particular, it's very interesting to see that it's more like the average is approaching the most likely in this case, because the transition is actually discontinuum, than the opposite, right? So I think for the analysis of this small and middle size network, and not only interdependent network, but also standard percolation, is quite indicative, this analysis, of the danger that just calculating the average outcome can lead. So I reached my conclusion. So I wanted to give you an overview about multi-layer network, and that capture the complexity of systems of a different type, and the fact that multi-layer network can encode more information than single network taken in isolation. And I discussed with you some of the results that we had in percolation, related to percolation. One related to the introduction of redundant interdependencies that can, in some sense, explain the advantage of having more layer to have a more robust structure. And another approach, which is this approach of large deviation theory, to study the risk of having dramatic cascade of failure. So these are some references, of course, the book, and yes, some of the codes are on my GitHub page. And I want to end here with a small additional advertisement that we have launched in the IOP journal JFIS Complexity, which is has a very inclusive scope. And so please submit your excellent research there. Thank you so much for your attention.
Thank you, Ginestra, for the nice detailed talk, and nice to see a new journal devoted on complexity. And so I hope some people will submit their papers there. So is it open to any contribution, or has to be physics?
Yes, so this is IOP that is hosting it. So they put, of course, physics, but no, the journal wants to be very comprehensive and interdisciplinary.
Okay.
So it really respond to the need to be quite open. But maybe you know, it is interested mostly on you know, scientific and methodological advances in complexity.
Very good. So other questions from the public? Maybe instead of writing to the chat, if somebody has a question, can just open the screen and talk. Any?
I have a question, but
Giovanni, please.
Yes, thank you for your nice talk, and Giovanni Naldi from Milano. And I have only two curiosity. The first one is you started, and your multi-network was a network where all nodes are replicated in each layers. It's okay. So also your results about the robustness is about this kind of multi-network. I mean, robustness where the nodes in each networks are the same, not the link, but are the same for each layers. And the second question is, you know that in the graph theory, it's possible to recover some information by using some algebraic, for example, eigenvalues or something like that. Is the same also for your multi-layer network? Exists something like eigenvalues, something like that?
Yes. So there has been a lot of research, in particular the group of Alex Arenas, Yamir Moreno. They have proposed what is called a supra-Laplacian. So this is practically just the Laplacian of this network. So this network with interlink. So you take the replica node you can consider as different nodes, and to the interlink you can give, for instance, a weight if you want, and you study the Laplacian of this structure. And then you study, as a function of the weights that you assign to the interlink, there has been a lot of focus on the Fiedler eigenvalue. And so is the multi-layer network, for instance, sustaining a faster diffusion than their single layer taken in isolation? Or you know, there has been also observation of phase transition in this kind of aspect. So this has been a very active research field. Most of the attention has been driven to this Fiedler eigenvalue. I have to say that there has been not much more studied. So, for instance, I've been interested for other reason, for other generalized network structure on spectral dimension and, you know, higher order Laplacian, but this has not been covered for multiplex network. Everybody focused on practically how the Fiedler eigenvalue change with this weight of the interlinks, essentially.
Thank you.
Okay, so other questions from the public?
Yes, I have one.
Please.
I'm Thierry. Can you hear me?
Yes, we can hear.
Okay. So, okay, thank you very much for the talk. It's quite inspiring. And so I'm wondering, well, if I got it right. So first of all, so I'm thinking about electrophysiology and on EEG recordings, for example. So there are quite many studies focusing on the functional connectivity, so how the different electrodes, the different nodes interact with each other. And there are plenty of works where people focus on some frequency bands, and they focus on how the functional connectivity networks for example, the alpha band, so it's just a particular band of frequencies, interact. So how does it look like, this functional network? It seems to me that here we can somehow extend the concept by focusing on different frequency bands. So one layer could be the alpha layer, and the second layer. I'm just wondering, well, it's of course it's much more a problem for us, but with this approach, actually we could extend the concept and go to interaction between the alpha layer and the beta layer. So I don't know what that could mean. It would, I'm not, maybe there is also already something about that. So I don't know how much this research field is diffused in the world.
Yes, most of the people that have looked at functional connectivity and multi-layer networks to capture that, they have adopted a representation of multiplex network to capture the temporal evolution. So they have, you know, a given set of frequency probably that they are focused on, and they look at the time series in time and the correlation average over a given time window, and they build this layer, and each layer is a aggregated network in a different time window. But yes, but this idea of having a multiplex network for representing the different frequency, I think is very interesting. I have the impression that maybe somebody else also told me about that. I don't remember exactly a paper with this, so I don't think that I know. I mean, the literature is really very big, but that I know, I cannot point you to a paper that has addressed exactly this. But maybe in some of the review of the Bassett, this could be mentioned or something like that.
Yeah, okay. That's okay. That's thank you for.
Thank you. Other questions on the talk?
I have a small curiosity.
Linda, please.
Okay, so about redundant interdependencies, you show that they boost the robustness of the multi-layer networks. The curiosity is how common are those redundant interdependencies in natural networks, for example, like in the one you show at the beginning, related to brain connectivity or cell molecule interaction?
So I think, yeah, okay, this is a very interesting question, but I think both model, the standard one and the redundant one, are kind of a stylized model. So speaking, for instance, with the author of this paper on brain connectome, the multi-layer connectome, one of the authors told me about this fact that, for instance, some of the neurons, they have some kind of activity that depends on the dosage that they receive about one of these monoamide. So practically, this is a lot of combinatorics, you know. And I think that probably this model, both the model, the standard one and the redundant one, are to be considered in any case a stylized one, but is a proof of concept in some sense that instead, if this multi-layer network can be used, maybe by biology, in order to, in some sense, constrain or adding more and more constraint on the activity on the node, but they can act as adding redundancies. So you can use that in using the combinatorics in both directions, right? So I think they must be considered a bit like a proof of concept. And of course, if you look at the given specific biological example, then you need to be a little bit more, you need to see if there are these interdependencies. But I think there is no evidence that one model is better than the other one in some sense, except the evidence that biological network can have many layers, and they might not be so fragile as taught by the other model.
Thank you very much.
Other questions in the public? No questions. I think we will thank. We are in perfect time. It's 5 o'clock. So we thank Ginestra again for this nice overview, which will be available on YouTube. So if you want to know about multiplex network, you can now connect to the channel of the Center for Complexity in Biosystems and listen again to Ginestra's talk or refer to it to your colleagues. Okay, so the next seminar, as I said, is on the 26th of February by Bernat Coromina Mutras. He will tell us about stem cells and modeling stem cells. So it's more biophysics talk. So the topics, as usual, will alternate between different fields. So thanks again, everybody, for listening, for posing the question, and we hope to see you soon, very soon. And
thank you.
The virtual applause.
Thank you. Bye-bye. Bye-bye. See you
Bye.
soon. Bye-bye.
Thank you.
Okay.
Ciao Ginestra.
Ciao. Ciao.
Bellissimo seminario, bravo.
Sì, la prossima volta un altro argomento, promesso, però c'è...
Va bene.
Ciao.